Hello everyone. In this video, we will have some examples regarding the time and space complexity of some selected examples. In the previous videos, we have studied how we can measure the efficiency of an algorithm, and we know that time and space complexity are the two keys we have for that complexity analysis. And we also know that we use the asymptotic notation to represent our results. So now in this lecture, we will try to work on some examples to see how these things work. Okay. First of all, I will follow the advice of George Polya from the 50s. Okay, so that great mathematician once said that, okay, it is better to solve one problem 5 different ways than to solve 5 problems one way. So that is why we will focus on just a single problem initially, and we will see different solutions to that problem. And I hope this will help us to understand those time and space complexity issues better. Okay, so let's start. The problem that we will be studying is rotating an array. So that is something simple. I believe most of you already have the information for that problem. But let me repeat it again. We are given an array. So let's say this is the array A, and we would like to rotate the elements to the left. Rotate left means if I'm rotating left by D positions, I will shift all elements to the left by D positions. But in that case, I will be overwriting the elements on the first D cells of this array. So that is what will happen to those elements. They will be rotating. For instance, if this is my initial array, okay, and if this is my initial array, and let's say I will be rotating it to the left by 1 position. That means that 8 will come here, 7 will come here, 0 will come here, 1, 5, okay, 9, 2, and this is 4, right? 4, okay. And what will happen to this element, the first element? So it will go back and will be inserted here. So that's the rotate left operation. And the question asks me to give a function such that given array will be rotated to the left by D positions. That means in my function, I will have 2 parameters. The first one is an array of size n, and the second parameter is how many positions I will rotate it to the left. Okay, so let's start with the naive solution. Okay, so that's the basic solution. It is always good to study the basic solution first. Sometimes maybe you may have heard that phrase, so first make it run, then make it run faster. And I like this way and I will be following it. Okay, so this is the most basic solution. So once I have an array and I would like to rotate it to the left by D positions, what I can do is I will rotate it to the left by 1 position and I will repeat it D times. In other words, if I would like to rotate this array to the left by 4 positions, I will rotate it to the left by 1, have the result, and then rotate the resultant array to the left by 1 again, and I will repeat this 4 times. And this is the function I will have. So let's see what it says first. So it says for k is equal to 1 to D, okay, just save the first position in a temporary place. Okay, so that's a temporary storage, because why? We will be overwriting that A0 very soon. And then what I will do is I will shift all the remaining elements to the left by 1. Let you see, so when I is equal to 0, what will happen? A0 will be equal to A1. right? That means I have overwritten A0, but no worries, it's already saved in the temporary variable. Once I shift everything to the left by one position, what I will do is I will insert the saved element, which is A0 to the nth. So this is the way it works. Now, we said that the time complexity of an algorithm requires counting the number of instructions in this algorithm. Let's do it line by line. Okay, so how many times this line will be executed? So that is a for loop, and k is equal to 1 to d. It's not that much hard to see that this line will be executed d times. Since this is a for loop, every line in this for loop will be executed d times. So that is why assigning A0 to the temporary variable, so this will happen d times, right? And then when I come to this inner for loop, for k is equal to 1, this will be executed n minus 1 times. For k is equal to 2, this will be executed n minus 1 times. For all d cases, this line will be executed n minus 1 times. So that is why I will say that this line will be executed d times n minus 1 times. Okay. Similarly, this is the inner instruction of this for loop. So I can say that this line will also be executed d times n minus 1. And then once this for loop is over, this line will be executed d times. Okay, very nice. So now I can just sum all these number of instructions and see the total number of instructions. I will have d plus d plus dn minus 1, dn minus 1 plus d. So this will make 2d n minus 1 plus 3d, right? Okay. Let me go one step further. So that is 2dn, right? Minus 2d plus 3d. Good. And this will be 2dn plus d. Okay. So this is my final number of instructions. Remember what we talked about the time complexity function. So this should be a function of the input size. And what are my inputs? I have n and I have d. Okay, so may I write it in this way? F and d is equal to 2dn plus d. Good? Okay. Actually, when we see this number, let's try to investigate it a little bit more. Okay, so what I expect that that number n will become larger and larger and larger, right? And d is always something less than n. That is why when you look to this function, actually, the dominant term, which will become higher and higher with the increasing value of n, is this part, right? And since the constants are not imported in our asymptotic notation, I can say that, so this function is in O(n) times d. Okay, so let's see. So I say that this is O big O(n) times d. Okay, and so let's remember our previous lectures. What is the limit of 2nd plus d divided by n? Okay, n times d. Okay, so this is when n goes to infinity. When n goes to infinity, what will happen is, so this limit will go to a constant. Remember the previous lecture that when that limit goes to a constant, so that means Okay, so the function that I'm looking for, that I'm investigating, is in big O of the denominator. So that's big O and D. Okay, so okay. I am just trying to do it in every detail so that we will be understanding it well. Okay, so now I have decided that the time complexity of this approach is big O and D. It is upper bounded by n times d. I would like to take your attention to one point. I know that d is always less than or equal to n. If d is equal to 1, this will be my best case for this algorithm, right? Because I will be repeating everything just once, and it will become a linear algorithm. However, when d becomes n, then this will turn out to be O n squared. So this is my worst case, and this is my best case complexities. You see, whenever I have an algorithm, I should always consider what would be the worst case and what would be the best case. Usually, we mostly focus on the worst case, and we can say that the naive rotate left algorithm is a quadratic time algorithm, okay, in the worst case, and it's upper bounded by this O and D. Okay. How about the space complexity? Now, when I see this algorithm, I would like to count how many extra memory space I will need to run this algorithm. Okay, what I will need. So this is my input, right? So this is my input and this is my input. In addition to this input, okay, excluding some variables, a, k, I, whatever. So I will need only one temporary position. In other words, this temporary location is just one cell in the memory. It doesn't depend on what n is. It doesn't depend on what d is. Since it doesn't depend on the input parameters, it is something constant. So the space complexity, I can say that it is constant. And remember, the time complexity was n times d. Okay. This is space complexity, and this is the time complexity. Very good. So that was the most basic solution, and let's try to see a bit improved version. Once you wrote the first solution, you will immediately observe that, okay, instead of doing it d times, actually, I know that every element will be shifted by d positions to the left. I don't need to do it in steps of one. What if I immediately move every element to the left by d positions? Surely, I should start somewhere that is beyond the first d positions. I mean, okay, in this example, I'm rotating left by 4 positions. Skipping the first 4 guys, what I will do is I will immediately shift this element by 4 positions, 1, 2, 3, 4. And this will go here, and this will go here, okay? So that is good. But what will happen? So the first D elements should be saved, should be stored in an auxiliary space. Why? Because we will be overwriting them, and at the end, I want to insert them to the vacant positions, vacant D positions that will appear at the right of this array. And here is the pseudocode for this one. Okay, so here is the first line. What we do is, in a temporary array of size D, we just store the first D elements of the array. And following that, what we do is we just shift all the remaining elements and minus D elements to the left by D positions. You see, AI minus D becomes AI. Good. And then at the end, with a second for loop, what I will do is I will just copy the previous elements stored in temporary array to there, to the last D positions on this array. Okay. I would like to take your attention to that point. Again, I'm using two for loops, but the second for loop is not inside the first for loop. Remember, it was actually, I'd like to show it to you. Here, the second for loop, okay, was inside the first for loop, but now it is not. Okay, so they are independent. Okay, so let's make again that counting. If you say that this line will be executed 1 times, or the number of instructions for the first line is just 1, that will be wrong. Why? Because with our theoretical model, we assume that all atomic operations take constant amount of time. So that means if in a line you have fixed number of arithmetic operations, logical operations, comparisons, branching, so that is fine. However, here, it is not just a single operation because I will be copying the elements from A to this temporary array. That should count by B instructions. That is equal to something like for I is equal to 0 to D minus 1, temp I is equal to AI. Okay, so that's a short version of this one. This is important. I'm spending maybe a bit long time to describing you this because whenever we write the pseudocodes, sometimes to keep something short, concise, okay, so we just combine such small for loops in just one little line, and that doesn't mean that it is a constant operation. We should always think about the lines. One mistake that we can make, for instance, so let's assume I have some algorithm here, and in some place it's as a call to a sort function. So that is just one line. Being one line doesn't mean that this is just one instruction, okay? So because since this is a call to a function, so the cost of this function should appear here. Okay, I just wanted to make this clear, and now let's continue. Okay, so the number of instructions for the first line is D, and then this one, this will take n minus D, right? So this will take n minus D, and this will take D, and this will take D. Good, right? So once we have all of them, okay, so what is my total complexity? So D plus n minus D plus n minus D, okay, plus D plus D, correct? Okay, so at the end, what I have here is 2n minus D plus 3D operations, right? And if we make the summation, so we will have 2n minus 2D plus 3D operations, and it will be 2n minus D operations. Okay, so this is the total number of operations that I will have. Okay, 2n minus D. Okay, so I can say that in terms of my input parameters, the number of instructions is equal to 2n minus D. I know that D is always less than n, or in other terms, the dominant term in this polynomial is 2n, right? And I can say that, so this is an element of big O n. You see? In the previous one, it was an element of, the complexity was an element of n times t, which can turn into n squared in the worst case, but now it doesn't matter, okay? So even if t is equal to 1, 2, 3, 4, 5, whatever, so you will be always doing it in linear time, okay? Both worst case and best case, so it will be in always linear time. So that is an improvement. Previously, it was O(n) times t, and you make it O(n) with this algorithm. So that is for time complexity. For the space complexity, what happened is, previously, it was constant. So let's see what happened now. In the previous version, in the naive version, we only need just one memory location. However, now I need an array of size d. That is why my space complexity had become OD instead of O1. In other words, I'm using more space to make my algorithm more time efficient. So this is called time memory trick, let me say. So actually in the upcoming lectures, we will have more time to investigate this approach, but just to warm up, I want you to see that. Okay, so this was the naive version, and this is now our new version, so temp array version. Good. What else? So it is good. I have a linear algorithm now in terms of time complexity, but my space complexity has increased. Wouldn't it be better if I do it in O(n) time, however, by not spending more than constant space? So this is my target now, okay? Time complexity will be O(n), and space complexity will be just O1, okay? Let's see. This is our third solution for this problem. This is a bit different. It says that what you will do is, when you have this array and the d number, so the size of the array is n and the number of rotation is d, what you will do is you will go and reverse the first d elements, then reverse the all remaining elements, and then reverse all of them. I will do it here. I will do it here. So this is my original array. So I reverse it. Okay, 0, 7, 8, 3. Okay. And then I will reverse the remaining elements. So this will be 4, 2, 9, 5, 1. And then I will reverse everything. Okay, so this will be 1, 5, 9, 2, 4, 3, 8, 7, and 0. And that is bingo, right? It is very interesting. Why? First of all, it is very easy to communicate. Reverse the first d elements, reverse the remaining n minus d elements, then reverse everything. Very easy, right? But it is surprising, because whenever you see this first, okay, whenever you hear about this solution first, it is not immediate to see that it works. However, once you think on it, I will not be providing the proof, but it is not that much difficult, okay? So you will see that actually it is the rotate by left definition by using the reverse elements, and it's always correct, it's always true. Why I am telling this? Because I would like to make you remember our previous discussion about the elegance. Okay, what was elegance? So that was something very simple and surprisingly beautiful, which is this solution for this problem. That is why that reversal, using the reverse operations for the rotate left, is a very elegant algorithm, and in real life, it is the most widely used version of all possibilities. Okay, so once we are caught with the beauty of this solution, so let's see how does the complexity works. Okay, let's see. First of all, for this solution, I'll be using two functions. I will need to use a reverse function, and this part is that reverse. Reverse is actually very easy. So once you are given an array, okay, you will be swapping these elements, and then you will be swapping these elements, and then you will be swapping these elements. If you have n elements with n/2 swap operations, you will be done, right? So if it is 1, 2, 3, 4, 5, so reverse 5 and 1, okay, so swap 2 and 4, okay, so 3, there's nothing to swap with, so this will be the reverse. Okay. What is the complexity of the reverse? It's not difficult to see that it is linear, right? Again, let's try to do it with our old-fashioned way. Okay, so while start is less than n, so if a is of size n, so that means this will be executed n times, okay? Actually, it will not be executed n times because start is incremented by 1 and end is decremented by 1 at each step. This will be executed n/2 times, okay? n/2 times, n/2 times, n/2 times. So in total, this will be n/2. And remember, n/2 with the asymptotic notation, we are always interested with the dominant term and we are not interested with the constants. So 1/2 times n, so that is O(n). Okay, so that is something linear, I know. Okay, let me just write it. So this is a linear solution. Now, what I will do with the rotate left, I will be calling this function 3 times. So that is O(n), that is O(n), that is O(n). You know, O(n) plus O(n) plus O(n) is actually O(n). Okay. Let me try to describe it in another way. I know that with this function, there will be n/2 swap operations, right? Since there will be n/2 swap operations, n/2 swap here, n/2 swap here, n/2 swap here, in total, I will have 3 n/2 swap operations. And swap operation is a constant operation, right? Actually, it includes just swapping two elements. So if you write it, so this will be actually just 3 memory movements. Okay, so 3 n/2 3 n/2 instructions. So that will make O(n) instructions. It is very good. Okay, now I hope we are convinced that so this solution, the time complexity is O(n). How about the space complexity? For the swap operation, how we do it? Okay, so you can see that T is equal to A start, okay? A start becomes A end, right? And then A end becomes T. Again, I only need just one memory location. That is why it is not dependent on the input size and the space complexity. The extra space that I will need to execute this function is O1. This makes that reversal algorithm to be better than the previous two algorithms. Just comparing the previous one, it was ON, but it was OD space. And D can go to, in the worst case, N, right? So you just remove this linear space necessity and made it just constant. And beyond the improvement in the space complexity, this algorithm is a very nice example of elegance in algorithm design. When you need to communicate this algorithm with your friend, it is actually very easy. As you might have already observed that among the last three algorithms, this one is the easiest for me to explain. Reverse the first t elements, reverse the remaining elements, and reverse all of them. So that's it. That's it. And that simplicity and surprisingly performance, so that makes it a very elegant solution. Okay, so let's continue with the fourth solution. This will be really a very suffering one. Okay, hold on. Let's start. It is interesting, but it is really a lot more complicated than the previous three solutions. At the end, let me tell you, we will see that this is a O1 time, ON time, sorry, O1 space algorithm, which is equivalent to the previous reversal solution. However, you will see that this is a lot more complicated. So let's start. Okay. This says that actually what I have is, I know once you give me the array and once you give me the parameter D, I can compute which element to move which location, right? I know this. And once I can calculate this, why not to do everything in one shot by using just a constant space? What I would like to say is, so let me show you. Okay, so let's assume maybe I should make this a little bit larger first, and then we will focus on the remaining algorithm. So let's assume this is my array, okay? And this is my array, input array, and I would like to reverse it to the left by 4 positions. Okay, what will happen? What will happen? I can compute that the element at position 5 will go to the position 1, right? And then position 6, so that will go to position 2. And position 9, okay, so it will go to position 5. So these are the easy ones, right? What else I know? I know that actually since this is A, and this will be rotated to the left, considering this array as a circular array, I will be able to compute that the first position will go to 6, 2 will go to 7, 3 will go to 8, and 4 will go to 9. Here, you see the demonstration of this sequence. It says that, okay, so who will come to first position? 5 will come there, okay? Who will come to the 5th position? 9 will come there, okay? Who will come to the 9th position? 4 will come there, okay? And you can just make such a chain. Programmatically, what you will do is you will save position 1 to a temporary location, saved. You will move 5 to position 1, and then you will move 9 to position 5, 4 to position 9, 8 to position 4. And once you are at the end of the sequence, what you will have a vacant position at the end, and you will be copying that element that you have already saved into the temporary location to this one. Good? Perfect. So once you see this, actually that seemed a very nice solution, and you decide to make one more example run. So let me just rotate the same array to the left by 3 positions. Again, doing the same, okay? So who will move to the position 1? The element at position 4 will move to 1. And then what will happen? So 7 will move to 4, and then 1 will go to position 7, and then what will happen? I will be repeating the same sequence again and again. That means, okay, I'm done with 1, 4, and 7, but I am not able to touch the others. That is a loop, a cycle, okay? Once you see that you have this cycle and you have not moved, you have not rotated the other elements, you start with the second element. Then you say that, okay, so let me start by 2, 5 will go to 2, 8 will go to 5, and what will happen? 2 will go to 8. Again, that's the cycle. Once you hit that cycle, you just break it and continue with the third position. And once you have it, at the end, you will again see the cycle. But the point is, you have already rotated all 9 elements. So now you are fine. With further investigation, you understand that that is because 9 and 4 are relatively prime. That means whenever you start from a position, you will hit the same position only after visiting all other elements. But since 9 and 3 are not relatively prime, and their greatest common divisor is equal to 3, what you will need is, you will need 3 cycles. You will start from the first position, then the second position, then the third position. You will be repeating the same thing. However, you will need GCD number of iterations. I will not go to the details why that is so, okay, but only I would like to show you the algorithm. Now we have the main idea. What we will do is, first I will compute the greatest common divisor of n and d, and then I will repeat this shift operation how many times, whatever that GCD returns me. Okay, so the GCD function, for the GCD function, what you can do is, actually it is here, and also I have copied another more clean version to here. So this is the Euclidean GCD. Euclidean GCD. You remember this from our previous presentations, right? And with the Euclidean GCD, actually, this is the best algorithm to compute the GCD. And again, it needs a bit more mathematical deep diving. But skipping that, let me tell you one thing. The worst case for the Euclidean GCD calculation appears when those two numbers are two consecutive Fibonacci numbers, okay? Fibonacci numbers. So if those two guys are two consecutive Fibonacci numbers, then the Euclidean GCD will have the maximum number of iterations. At each iteration, the result is the resulting number will be less than the previous guys by at least 1 bit position. Again, I don't want to complicate things. Maybe that is too early for us at the time being, But later, we will see that actually each Fibonacci number, the kth Fibonacci number, has log n digits, okay, some sort of, okay. And that is why you can assume that the complexity of the Euclidean GCD is just log n, okay. Let's keep this in mind and we will go to our main algorithm. Okay, here I'm having this line and I know that this comes with O log n complexity. Other than that, what I will do is I will be repeating this for loop how many times? GCD times. And then I'll be doing some operations here. If you would like to make the same analysis counting the instructions here, it will be more difficult, okay? It will be more difficult because it will be a bit more difficult to count how many times this for loop will be executed and anything. But in such cases, you may think with a different perspective. At the end, what will happen? Each item in this array will be moved to its final destination in just one step, correct? Yes. And I have n items. It doesn't matter how many times this for loop will execute, but at least each item will be executed at least and at most exactly one time. So that is why whatever happens here, it is linear, okay? And the total complexity is On plus O log n. So the dominant term is On, so that becomes On. That is On. And what about the space complexity? Space complexity is still constant. That is why this algorithm has the same performance with the reversal algorithm. To the best of my knowledge, if I'm remembering correct, if you do it with the GCD version, that might be even a little bit more quick, more speedy than the reversal one. However, you should always consider, would it worth the effort to have this torture, to have this performance speed up? When compared to the reversal, so this is a lot more complicated, and assume how difficult will it be to communicate with your friend to just develop this solution. Good. And so let's continue. Moral of the story. So we are done with the 4 different solutions for the rotate left algorithm. I suggest you to think how you can just create variations to support rotate right, okay? And if you check internet, you will see that there are a couple of other solutions that are a bit more complex maybe, but I think that is enough for this rotate left to just study the basics of algorithm analysis. This slide is just to show you that actually the main point while computing the time complexity of the algorithms usually requires focusing on the for loops. So that is why I say that watch the loops always. Let's see this mystery function. This is my function, and I would like to compute its complexity. There are 3 for loops, and these are cascaded for loops, which means the second for loop is inside the first for loop, and the third for loop is inside the second for loop. That means the line that will be most executed in this program will be this line. And if I can count how many times this line will be executed, then I can compute the complexity. This is my main question for this analysis and how I can do it. These are just some small tips for you. First, when I look to the mystery function, it is not very immediate to me what it makes. Okay, so what is it computing? That is why I prefer to study it with a small number first. So let me say, first, I will assume that this n is equal to 4. If n is equal to 4, then what will happen? I have an I variable, and this variable will take values 1, 2, and 3. Good. And for each one, whatever it is, j will take the values from I plus 1 to n. If I is equal to 1, then j will take values 2, 3, and 4, right? If j is equal to 2, it will take, if I is equal to 2, j will take values 3 and 4. And when I is equal to 3, the only value that j can take is 4. Good. You see, my list is expanding. And then I come to the third for loop that tells me that value k will take values from 1 to j. So when j is equal to 2, it can be 1 and 2. When j is equal to 3, it will be 1, 2, 3. When j is equal to 4, it will be 1, 2, 3, 4. Okay, this is. And similarly, 3, 4, and 4. Now I can compute how many times I will hit this line, right? So it requires the summation of all those cases. Okay, I will hit to this line 2 times here, plus 3 times here, plus 4 times here. And then 2 times here, 3 times here, and 4 times here, and 4 times here. In other words, this will be 2, 3, 4, right? 3 plus 4 and 4. And I will need to sum all of them. If I generalize it, since 4 is my n value, this is my summation. And when I see this, I observe that this is equal to 1 times 2 plus 2 times 3 plus 3 times 4. You see, this is a very well-known sequence, and we know that it is solution. The closed formula for this summation is this one. To show you another way of approaching this, what I can say, instead of trying to understand what's going on and trying to come up with such a representation, you can go purely theoretical, and you can say that what will happen? I will take from I to n minus 1. J will take values from I plus 1 to n, and k will take values from 1 to j. And there is a constant operation here. I'm just trying to make the summation. For k is equal to 1 to j, summing up that much of 1 values, okay, so this will be equal to j. You solve this. And what is this? Okay, it is equal to this one. You are done with this guy, and if you just solve it, you will come to that position. What will it say me? So that is something n cubed plus something, right? So what I will say, this is equal to, what I can say is, it is O n cubed. Good. These are all for the sequential algorithms. What will happen if the algorithm is a recursive one? Let's see a recursive function. So this is the recursive function to compute n factorial. Okay. You know, n factorial is equal to n times n minus 1 times n minus 2. Okay, so this will go up until 1. And n factorial is equal to n times, what is this? This is n minus 1 factorial, right? So you can use this fact. That is why with this pseudocode, we are using that fact. If n is equal to 0, I will return 1 because I know that 0 factorial is equal to 1. You can even make this, if n is equal to 1, return 1 as well. But anyway, so this is written in that way. Else, what I will do, I will call the same function. Whatever it returns, I will multiply it with n. That means if I'm counting the number of multiplications, okay, number of multiplications for the input size n is equal to number of multiplications for n minus 1 plus 1. So this is my recursive formulation of my cost. How you can solve a recursive definition? So you can just substitute, right? mn is equal to mn minus 1 plus 1. So what is this? This is mn minus 2 plus 1. What is this? mn minus 3 plus 1. Okay. So if we go in this way, we will go up until 0, and we will see that actually we will be stacking up n multiplication operations. So that is why I will say that this recursive function has a running time complexity of O n. And for the space complexity, there is no increase in the space. Actually, it's not using any auxiliary space, so it is constant. But this is the way we should approach the recursive algorithms. First, we should come up with the cost represented with a recursive formula. That's it. And then once I have this recursive formula for the cost, what I will do is I will try to solve it to come up with a closed representation. That was a bit easy. And the next solution is something we should all know well. Okay, so that is the Tower of Hanoi problem. That's a very famous problem. I guess many of you know it, have faced with this algorithm with your previous courses. But let me repeat it again. What we are trying to do, we have 3 towers. In the first tower, let me say A, I have n disks. The smallest one is on the top and the largest one is at the end, and the disks are sorted according to their sizes. In other words, at the top of a larger disk, there appears always a smaller size disk. You can never allow to have something like that. So let me have a small disk here and a large disk here. So this is forbidden. Okay. And what is my aim? I'm trying to carry all of those n disks from tower A to tower C. Okay. And how many movements, how many disk movements will I need for that? First of all, let's try to, again, understand the problem. Okay, so let's assume I have just one disk here. Okay, so if I have one disk, then it is very easy. I will just take it from there and put it to C. So this is just one step. Good? Yes. Okay, what if I have 2 disks? 1 and 2. So this is there, this is there. Okay. I will move the first disk to this one, right? And then I will move the larger one to the target. And then I will move this guy to the top of the other one. How many movements did I make? So I make 3 movements, right? So when I have, so let's show it by T, when I have T only one disk, what I had is T1 is equal to 1, right? And then what happened with whenever I have 2 disks, it is equal to 3, right? Okay, and then what will happen when I have 3 disks? So let's try to see it. Okay, I have 3 disks here, and I have these other vacant towers. Okay, so what I should do is I'm trying to carry everything from this place to this place. Okay. If I can carry the top 2 items from A to B first, okay, then I can move the large disk to C and then move these 2 guys to the top of this one again. Why I am trying to tell you in this way? Because I know how to move 2 disks from A to C, right? But does it matter moving 2 disks from A to C and A to B? In terms of steps, it will not differ because these are just identical towers. Instead of using this one as the auxiliary, if I use tower C as the auxiliary, then I will be moving 2 disks to the B easily. Once I do this with how many steps? T2 steps. What I will need is, I will need an extra step to move the large disk from here to here, right? Good. And what else? Now I have the large disk here and 2 disks here. What I will need? I will need to move these 2 disks to the top of this guy again. And this will again take T2 steps. Moral of the story, to move 3 guys, I will need 2 times the previous one, T2, right? And then plus 1. It is this representation. Okay. Once you see this representation, what you can do is to find its closed formula. What I will do is I will just replace Tn minus 1 with Tn minus 2, and then this will go to Tn minus 3. And then you will see that once you do these substitutions, you will come up with this closed formula, 1 plus 2 plus 4 plus up until 2 to the n minus 1, and that becomes 2 to the n minus 1. Okay. Then moving n disks from A to C will take 2 to the n minus 1 steps. That is interesting because this is no more a polynomial function, right? So 2 to the n minus 1 is not an element of On, is not an element of On square, is not an element of any On to the power of C. This is not possible, okay? This is something exponential and requires exponential steps. In other words, this is a member of functions in the exponential big O set, 2 to the n. And 2 to the n grows very fast, if n is equal to 64, it will take too long to make this carry operation. And there are some histories beyond these numbers, but I will not go into those details. This video, I believe, has already been very long to you, okay, but I hope it helps us to understand how we do the algorithm analysis better. We will have some more examples and some more details in the class. Take care, and please spend some time to watch the video again, maybe if there is something missing, and please read the regarding chapter from our textbook. See you in the class. Thank you so much.